I was trying to help. I was trying to help somebody he like had the 13 out of the 14,
Yeah.
right?
Hmm.
But since I think my theory was since he put everything like A, B, C and everything in numbers,
Okay.
when I taught him how to do like the matrix and implement the function, I
Yeah.
think since he put all the numbers rounded by himself in the calculator, then maybe that's why he was getting them wrong. But it
Okay.
was just weird to me that he was still using the variables and MATLAB was giving him right. And he set up the equation the same way I did,
Okay.
and he still didn't get it right.
I was having that issue. It was weird, but then I changed the format from a decimal to using E, and it took the answers.
So yeah. So I'm gonna add back points for that last part. So 13 of 14. If you didn't get the last one, I'm gonna go ahead and add onto it. The reason is this: I wanted to have a quick discussion about it. So whenever you guys start struggling with something like that, feel free to start DMing me right away, because if there's a problem in the way that the problem is instantiated in MATLAB or whatever, I need to know that before like 11 o'clock tomorrow night, or the night that it's due or whatever. But if you find it and you think there's an issue, feel free to reach out. It's, generally it's your right as a student to be given things that work, right? That's the way things are supposed to be. So if you find an issue, now of course the problem is that you're a debate in your head about, is it my issue or your issue, right? And that's the,
Exactly.
and that in particular, I will say, the problems are checked, right? So we know that things are good, but occasionally tolerances are an issue. All right. And this is a case where tolerance was an issue. So in this particular instance, all right, well, we're going to add it back because we didn't have the time to be able to catch it. Okay. But the issue that came out in this particular case, if you, I'm going to use this as an example. Okay. All right. So I got an Excel. I got two numbers in Excel. All right. If I wanted to add those two numbers, what would you do?
A plus B, C
Yes.
Equals sum.
Yeah. Equals sum, or I would do A plus A1 plus B1, right? You would not probably go to your calculator and write down that number, I suspect, right?
Mm-hmm.
You could, nothing wrong with that, but you probably wouldn't do it that way. So one of the things that I noticed is that in some of the problems I got from people, this was one we got towards the last minute where somebody was having that particular problem. So everything was right except for their expression. And if you look at their expression, this is number one, that's the right format of the expression. Okay. This person's got the right format, but they weren't getting the right answer. So here I notice what's going on right here. So if I look at their results, they just dropped in numbers here. So that means that somebody did math in a calculator to drop in A and B and then alpha and omega 0. Again, nothing is wrong with that, right? I'm not criticizing you for doing that. Nothing wrong with it. But if you look, for instance, at the way the answer actually looks, right? Here's how I did it. Same way I think of it that way in Excel, right? If A is 1 over R times C, then I'm going to make a variable called R. I'm going to make a variable called C, and then I'm going to drop that in for A. Right? I'm going to drop in the equation there for A. I'm going to drop in the equation for B. And I compare that to saying, well, if I told you to add two numbers in Excel, you wouldn't add those numbers in Excel, right? You wouldn't do that on your calculator and then drop them in there, right? You would use a formula again, right? So this is a different way of thinking. And again, nothing wrong at all with you doing it where you just put in the result of some calculation. I'm just trying to tell you that, if you look at it from this perspective, you would start to say, well, that doesn't seem like it makes sense for me to do it that way. So I'm just trying to encourage you to do it that way. All right. Let me see. All right. So if you do it that way, so what I did was I actually took someone's code. I took my code here that we wrote for the solution. So this is the actual solution code. And then I took that person's code. Okay. And so I'm going to go ahead and run mine here real quick. So
I got the right answer without putting J for S1 and S2. Is like,
yeah, you didn't need that. I mean,
okay.
it's not part of the, that wasn't part of the question, right? So here's what you get. A lot of people said they saw that. Now I'm going to try, this is the code from the guy that, that we had that submitted this, and I'm going to create this figure 4. So if I do, all right, so I changed, all I did, this is where it's hard coded in, right? So I'm going to run this guy real quick. Oops. All right, and there it is. So this is what the guy that submitted it to us did. This is what my code did. So those are the same, aren't they?
Yeah.
They look like they are. Yeah. So let me plot these guys. So what I have here, this is the difference between them. All right, figure 3. Figure 4 is going to be the percent difference between them.
They kind of look a little bit different though. Just
They
like
do.
tiny.
They look different because you know there's a difference.
That might be true. Too.
If I just told you, you wouldn't probably think that. I don't know. So this is, let's see. Get all this stuff out of the way. All right. So the figure 1 is my answer. Figure 4 was the student's answer. Figure 3 is the difference between them. All right. That is because of the hard coding versus the non sort of parameterized version of the code. Again, I don't want to mark anybody wrong for doing that, right? And that's why I said, I already said before you asked the question again, I will add points back in this particular case, all right, for people that didn't get that. All right, but I just wanted to point this out. That's why that issue's coming up. So, you know, again, if I wouldn't even, when we do this, we check our answers, it wouldn't even occur to me that this kind of an issue would occur, right? The reason it's happening, I think, in this case is because if I take cosine of a small number, if there's a small difference between the numbers, so omega times t, if your omega was hard coded and mine wasn't, there's going to be a small difference. The sign of that small difference can potentially become a large number. All right, and that's why it's doing that. If you look at the percent error, there's the percent error. All right, so in other words, you look for some reason, and I know why, when there's issues probably near the 0 crossing, the issue becomes apparently there's a 10,000% difference at some point. Now we have a way around that when I set the tolerances, right, to be able to fix that problem. But that wasn't set in this case. And that's why I'm going to add points back. All right, so I'm trying to emphasize that point about I will give everybody points back on this particular problem because we should have set the tolerances larger. But again, I wanted to point out that the reason why that's the case, the reason why you were hitting those issues was related to the fact that we hard code, or that I variabilize these things, whereas you guys quote unquote hard code it. Where in other words, you're doing calculations in your calculator and dropping them in there. All right. I would encourage you not to do that moving forward. Now, you may not be comfortable with that, and I get that, right? But slowly but surely make yourself comfortable with that kind of thing. All right. Any questions about that? All right. All right. As far as I know, that was the only MATLAB issue that came to my attention towards the end yesterday. All right. Any other glaring MATLAB issues that you guys were aware of?
I ended up just making a matrix in MATLAB, and it worked out fine. But when I tried doing the matrix for, I think it was problem 3, and this might have been what Eli was talking about a second ago, and I rounded to like 5 decimal places, and it still didn't take it for my A1 and A2 values.
But we don't even ask you for the A1 and A2 values.
I mean, those were just the only things that changed between hard coding the matrix, like
We
on
don't
my
even, but
calculator
we don't
versus
even, we don't
putting
even
it-
check, we don't even check for the matrix though. But that's not a requirement.
But I
But
mean,
like you
when
needed the A
implement
values for the
function,
final answer.
Yeah. You
So, so the
question.
so the thing is, what was coming up wrong? Was it the final answer?
Yeah, yeah. I mean, I ended up getting it once I just made the matrix inside of MATLAB.
Yeah.
But
So what we'll do is in this particular case, it's not many points. I mean, I don't know, I think it's like 1 point or 1.5 points for the last part of the problem. But if you got all but the last part, we'll add in the points for the last part for everybody. All right. And we'll do that in this particular case. Because I think your issue, I don't know, was that Clark? Who was?
yeah,
Yeah, Clark, I think that was you probably were running into the same type of issue.
yeah. I mean, I definitely think that's what it was.
Yeah. Yeah, I think we can reset tolerances in a particular way. If you guys see real issues like that, I would don't be shy about DMing me about a problem that you think exists like that. We will do our best to try to get it addressed. All right. Okay. All right. Let me move onward, I guess. All right. So we started talking about full screen here. All right. So we've been talking about sine waves and phasors and all of those concepts. All right. And we introduced this really important concept the other day called impedance. So basically in the last week, we've gone through and introduced these three ideas. So the idea of sine cosine waves, this idea of phasors and the idea of impedance. And we said, we define everything in terms of which of the two, sine and cosine. We define everything in terms of what? Which one of the two?
Cosine.
Cosine. All right. Yeah, we use cosine as sort of our reference. Okay. And we're going to continue to use that all throughout the semester. All right. And we introduced this idea the other day of impedance, right? What was the variable I used for impedance? Anybody remember?
Z.
Z.
Yeah. Z. And so I always do my Z with that little line in the middle. Okay. So Z, and I always put this under bar, this bar underneath of it there. It's not a vector per se, but it's the phasor. I don't know. We used to do that when I was in school. In the book, you'll see it in bold, right? Just like you would see vectors in physics. It'll always be in bold. What we defined the other day is I derived the first two of these, right? Basically, the impedance for a resistor, the impedance for a capacitor, and the impedance for an inductor, right? I didn't derive it for the inductor, but basically, we have this relationship in general. The phasor voltage equals the phasor current times the phasor impedance. All right, that is Ohm's law in a general case. And I said in particular, this idea that V equals I Z, right? That only applies in a certain case. What case does that apply to? What special case does that apply to? What has to be true?
It has to be in steady state.
It has to be in steady state, right? So circuit has to be in steady state. What else has to be true? That's
AC.
half of it. Not just AC, but what type of waveforms do I have to have?
Sinusoidal.
Sinusoidal. Yeah, they have to be sinusoidal, cosinusoidal. AC in general means more than just sine waves, right? And that you're correct. We're talking about AC circuits, but in particular, sinusoidal steady state. I need sinusoidal inputs, and we've said those are super common. Okay. All right. So
the meaning of underlining VIZ.
What I said is I write my phasors with this underbar, right? That's always the way that I'm going to write them to differentiate that it is a phasor. It's kind of like when you learn vectors in physics, right? If you look at a physics book, vectors are always bolded. But when you write vectors like the velocity vector, you normally do it with a little arrow on top, right?
Yeah.
It's the same idea.
Okay.
All right. It's really kind of to differentiate from the fact that it's not a vector, right? It's a phasor. It means something different than a vector does. All right. So to then we want to begin to try to use these things, but when we do so, basically, the important thing is when I give you a circuit, circuits exist in what I call the time domain. In other words, the real world that we live in. You apply a sinusoidal voltage source, and I have a resistor and capacitor or whatever. That, you know, so if I look at the voltage in a circuit, I will never see a phasor, right? I mentioned this the other day. I said, you stick your hand in a wall socket, you'll feel it at 60 hertz, right? Don't stick your hand in a wall socket, but if you did, you'd feel it at 60 hertz, right? In other words, if I look at the voltage on an oscilloscope, that voltage changes and fluctuates as a function of time. It's one value now, it'll be a different value a period later, 2 periods later, so on and so forth, right? But the important thing is when we go to the phasor domain, I say I represent this thing how? What did I say? I don't do it in the time domain, right?
The complex plane.
Complex planes. This is the real and imaginary part. This is a for all intents and purposes, this is an imaginary world, right? This is real, and this is a way of thinking about the real. All right, it makes our math easier, but it is not a real thing, right? There is not a phasor that exists that I can measure in the real world, but there are voltages as a function of time that I can measure in the real world. All right. So what we got to do is we got to map the circuit over to the phasor domain, which we'll do here today with some examples. And then we can start doing all the usual tools, mesh, nodal, superposition, Thevenin and Norton, like we talked about at the beginning. All that stuff kind of comes into play. Okay. All right. So we're going to try to do some problems today to start to do that stuff. But I want to remember a couple of things because the other day, as I was talking about this, it sounds like you guys were a little bit unfamiliar with complex numbers, or you're just beginning to remember them. All right, so let's say I've got two complex numbers, A and B. All right, so let's say, how do I write A and B? I guess I'll say it this way. So A and B, if I want to write those as in rectangular form, I would say I have the magnitude of A times the cosine of the angle of A plus J times the magnitude of A times the sine of the angle of A, right? You guys have seen that, correct?
Mhm.
Okay. All right. Let's say I do the same thing with B, right? So B is this guy plus J, magnitude of B, sine of the angle of B, like that. So if I say to you, okay, well, I want to multiply those numbers, right? What's the best way to do that?
Put them in exponential.
Yeah, put them in exponential form. I said even talked about that, but that basically means once I put them in exponential, what's the result going to be? What's the magnitude of this result?
Magnitude of
Multiple of A and B.
Yeah, magnitude of A times the magnitude of B. And then the angle of the result is going to be what?
Addition.
Yeah.
Angle A plus angle B.
Angle A plus angle B. Okay, like that. Now, if I said, let's do A divided by B, what would that be?
Same.
magnitude of A divided by magnitude of B.
Yep.
Angle A minus angle B.
Yep. So I'd say the angle of this guy is the angle of A minus the angle of B. All right. Like that. Okay. Now, one other way we say that we write these. So I I'm saying this guy is magnitude A, angle of A, magnitude of B, angle of B. The other way to write these that you've learned with Yahoo is what? You should have learned this with Yahoo.
AE to the J omega.
Yeah, Umang, you should know that, right? I know that because I taught that to you. I went last semester. I want to see if who's taking 2254 right now. Have you guys seen this in 2254? I can say this is the magnitude of E to the J angle A, like
Yeah,
that.
we've seen that.
Yeah,
Yeah.
we've seen that.
All right, good.
We've done a lot of converting between the three forms.
All right, good. All right, so now we're actually going to use it. So I've got those. Those are our three forms. I'm not going to spend a whole lot of time on this one, except to say that that's one way that I can enter problems into MATLAB to try to do the analysis. Okay. All right. So we're going to need to know all that sort of stuff. All right. Let me ask you this: if I gave you Z equals J omega L, and I gave you Z, I'll write it this way, Z sub C equals 1 over J omega C, okay? And I wanted to sketch those in the complex plane. All right, here's real, here's imaginary. Where does the impedance of the inductor go? J omega L, where is that guy gonna be?
Is he in the first quadrant?
It would just go straight up the imaginary axis.
It
wouldn't
goes
it?
straight up, right?
Yeah, so
Because it's purely imaginary,
Oh, I see what you're saying.
right? So in other words, I could also say that that guy is omega L angle what?
90.
Yeah,
90.
or 90.
90. Yep. Okay. Now 1 over J omega C, that's I can't, that guy doesn't have a straight up angle because he's not in rectangular form, is he? 1 over J omega C.
Not really.
How do I put it in rectangular form?
Multiplied by the conjugate.
Multiply top and bottom by the conjugate, right? So multiply top and bottom both by negative J. So what happens if I do negative J times negative J? What's that become?
-1.
positive.
Yeah, so sorry, I should be careful. J times negative J becomes,
Positive 1.
yeah, positive 1, right? So that becomes omega C, and then on top I get a minus J. All right. Where is that guy?
Pointing down.
Pointing
Bring
down.
down.
Yeah. Right. So this is ZL. This is ZC. Okay. And this guy I could write his magnitude is 1 over omega C, and his angle is what?
-90.
Negative 90. Yeah, negative 90. Okay. Where would a resistor be? So if I said Z sub R is a resistance, where would that be?
It would be along the real axis.
Yeah. And which quadrant would it go? Or which with a positive or the negative real axis?
Positive.
Positive. Has to be positive. Otherwise, I'd be talking about a negative resistor, right? And that doesn't happen. All right. So I have Z sub R would be that guy. So those are the only directions I can really ever have. Okay. All right. So we're going to get into some examples here. All right. So what I've got is a circuit that has R is 0.1 ohms, L is 1 millihenry, and then I've got this is my input voltage. Okay. So in other words, like I said, in the real world, it's going to be a sine wave, right? Or cosine wave. And what I need to do is to transfer that over to the impedance world before I can start to do my analysis. Right? In the time domain, what this would mean is I have V in and I have L and I have R like this. If I stay in the time domain where this guy is 3 sine omega t plus 45 degrees, and I said, I want to figure out what, let's say what I of t is. How would I have to solve that problem? If I stay in the time domain,
Is that an inductor or a resistor on top?
that is an inductor.
Okay.
All right, does that look better?
Yeah. So
All right.
how we solve for current?
Yeah, how would I solve for current if I stay in the time domain where this guy is a function of t, where this is omega t?
Well, you can use the VL relationship, right? You can just
Yeah. So
VL
basically,
over-
I'd go ahead and I'd write out, you know, KVL, and this would become a differential equation, right? So it'd be L di by dt
Mhm.
plus I times R. That would be how I would solve for I. And this guy has, we said, two components. What's the transient component look like?
Always
E
the
or
condenser.
AE to the ST.
Yeah,
Negative
AE to
ST.
the ST. Yeah, it always becomes AE to the negative T over tau, right? And then the other component of this is going to be some B cosine omega T plus phi. Now, what's true? So I was just saying, this is the steady state or particular solution. And what are we saying is always true about the steady state solution? Well, of those three things, right? So the amplitude, the frequency, and the phase, which one is guaranteed to be the same between my source and whatever quantity I'm looking at?
The frequency.
The
The
frequency.
frequency.
Frequency is always the same. Phase might be different. Amplitude might be different, but those things are always going to be the same. All right. Or the frequency will always be the same. Okay. So what we're saying is we only care about the steady state. Doesn't mean the transient doesn't happen. Just saying when we go into this approach, we're just saying we're not going to solve the differential equation. We're just going to worry about the steady state case. All right. So in that case, I want to figure out what the current's going to be. So I got to take this circuit up here. This is my time domain circuit. All right. And I want to put it into the frequency domain or the impedance domain. Okay. So I'm going to call the impedance or phasor domain. Phasor domain. Now it's the same thing. It looks the same. All right. Except if I called this L and I called this R, this guy I'm going to say now is ZL. He's represented by his impedance. And this guy is represented by his impedance, which is just simply R still. Okay. And what would I replace this VN with?
It's gotta be cosine.
Well, it's got to be cosine, and I'm going to replace it with its phasor, right? VN,
Oh.
its phasor. Yeah, and so we got to figure out what that phasor is going to be. But basically what I got to do is I got to transfer the circuit that I've got. I got to transfer it over to the phasor domain, which means that I got to figure out the phasors for all my sources, and I got to figure out the impedance of all of my components. Okay. So yeah, you're right. I have 3 sine, and let's see, I had some things here. I said 3 sine omega t plus 45 degrees. So the first thing is I don't know what omega is here either, do I? So what is my omega? I've been told that the period is 10 milliseconds. So how do I figure out my omega?
2 pi times 1 over t.
2 pi times 1 over t, right? Omega is equal to 2 pi f, and f is 1 over t. So that's 2 pi over t. So in this case, with 10 milliseconds, that's going to be approximately 628 radians per second. All right, approximately that. All right, now I have then 3 sine omega t plus 45 degrees. Okay. All right. So what do I have to do? I got to transfer that to get a phasor. Can I do phasors with sine waves?
No.
No, I got to get them over to some equivalent cosine. So 3 cosine omega t plus 45 degrees. And then there's got to be something I change to it. So the way that I think about this always is you can look up the trig identity, or I just draw for myself. This is sine and this is cosine. What do I have to do to cosine to turn it into sine? What kind of shift do I need? So here's
So you have to
cosine.
add 90.
You got to add 90.
Subtract 90.
Subtract 90, right? If I subtract 90 degrees, I would take this peak and I would move it to here, right?
Oh,
You didn't
yeah.
see that. I'd take this peak and move it to there. That's subtracting 90 degrees. You guys follow that?
Yeah, that makes sense.
So 90 degree, so subtracting an angle means that you move it to the right. And the way that I think about that is that means that it happens later in time, right? So negative, it's like I'm subtracting time. The peak happens at a later point in time. This is t equal to 0. This is t equal to something positive. This is at a time later, right? It's a time in the future. So I'm going to subtract 90 degrees. So that means that this guy is effectively 3 cosine omega t minus 45 degrees, like that, okay? What is the phasor then for Vn?
3 angle negative 45.
3 angle negative 45 degrees, okay? So we've got that set up. Now, if I want to figure out the phasor for the current, so again, I'll redraw that circuit. All right, here's Vn. All right, here's L. Here's R. All right, if I want to figure out the current, again, I want to know what it is in the real world, but I can solve for what the phasor is, right? And I said, this is Z sub L. This is R. How can I figure out what that current is with this approach?
V in divided by the CL plus R.
Yep, I'm going to treat everything exactly like it's a resistor. And I'm going to say I is V in phasor divided by ZL plus R, like that. That is now the phasor for the current in the circuit. And if I want to figure out what the actual I of t looks like, so, in the original circuit, I want to know what I of t is. Well, what I got to do is I just got to take that phasor and I got to convert it back. Okay. All right. So what if I want to go through that process, what should I do next? What else? What do I need to do before I can figure out this phasor? What do I need to compute?
Z of L.
Z of L, right? I got to figure out that impedance. So ZL. All right. Now, what's the formula for that one? Anybody remember? You can go back to the slide, but anybody remember?
JL omega.
Yeah, J omega L. All right, J omega L. So basically what I got to do is I got to plug in J and 2 pi times 1 over 0.01 times, in this case, my L value was 1 millihenry. So I say times 0.001, like that. That is now the impedance of that guy. So that will have a number and it will have an angle. What's the angle of that guy?
90.
90, right? So this guy's going to have a magnitude and an angle of 90 degrees. All right. Now, so what I did, this is what I want to take a look at here. So there's my expression. And I'm going to move this over to the side. And now what I'm going to do is I'm going to bring up the way that I did this, which is in MATLAB. Okay. So what I did was I defined all of the key variables for myself here. So I defined L as 1 e to the minus 3. You do this exactly like you would in the TI calculator, right? 1 e to the minus 3 is 1 millihenry. This is the same thing as if I said 0.001. Okay. And then my R is 0.1, and then I defined for myself, well, I was told that the period was 10 milliseconds. That's 0.01. So I defined my omega. Now, what I also did here was I defined for myself what the phasor was. All right, so let's see what's going on here, right? So I basically wrote we said before that the phasor for Vn was 3 angle negative 45 degrees. Okay. So if I wanted to put that in exponential form, right? How would I write that in the exponential form? What times what?
Just 3e theta, which is 45. Negative 45.
Negative
sorry.
45. Yeah. 3e to the j, negative j, 45 degrees. Okay. So what I did here was I entered it that way in MATLAB. Okay. Now, critical thing here. What am I doing in that line of code, line 6?
Change to radians.
I'm converting it to
Degree.
radians. Yeah, I'm multiplying this guy by pi over 180, which is to say that, you know, there's 180 degrees in pi radians. So if I take, you know, if you take an angle in degrees, right? So 45 degrees times 180 degrees over pi radians, that's our conversion factor that we need. Okay. So what I did was I converted that to radians. The reason I did that is because MATLAB expects everything to be in radians. So when I do that, what I'm going to get is my Vn right here. All right. So I write it that way. So let's take this guy right here and let's evaluate that code. All right. And let's see. So let's see what I get for Vn. There's my Vn right there. All right. It says 2.1213 minus 2.1213i. Okay. Where is that guy located in the complex plane?
Quadrant 4.
Quadrant 4. Yeah, it should be at negative 45 degrees. And I can tell looking at that that's at negative 45 degrees. But let's say you couldn't tell, right? MATLAB has two commands. If I told you guys this, here's a complex number, and I asked you to find the magnitude of that complex number, how would you do that?
Do norm.
ABS.
ABS.
Yeah, there's a command called ABS that'll do that. Now, you might know this as you could take the real part squared plus the imaginary part squared, right? That's sort of the way you initially learn that. But if I take the absolute value of it, that's MATLAB's way of doing the magnitude. It tells me that the magnitude of that is 3. Okay, just like we said it was over here, right? We said that it was 3. And then how do you find the angle of a complex number? Not a MATLAB way, but what is the way to find the angle of a complex number?
Arc10 A B over A.
Arctan of the imaginary part over the real part, which I don't recommend ever doing, because that only works in some cases, right?
Yes, because it depends on which coordinate system you're in.
Sometimes you got to add or subtract 5.
Sometimes I got to add or subtract 90 if the angles are in the second or third quadrant, right? And that's the kind of stuff that if Yahoo does the same things I do in 2254, that'll get half of you wrong on the exam. All right. So MATLAB takes care of that. It has a function called angle. All right. So I'm going to say angle of Vn. And all of MATLAB's default stuff is in radians. So it says it's at negative 0.7854, which if you remember your radians, that is negative pi over 4, right? But if I don't like that, I can multiply that by, how do I go from radians to degrees?
180 over
80
pi.
over pi.
180 over pi. Yeah. And boom, I see negative 45 degrees. All right. So my Vn has the right magnitude here, and it has the right angle. All right. Exactly like we would have said it should have been.
It's also a MATLAB function you could use, a RAID to degree.
There is. There's a MATLAB function that probably could tell me what I'm thinking right now. There's a MATLAB function for everything. I don't know. There's an app for that. So I actually included that. If you look in my code, this percent sign is a comment, and I put this degree to rad, and there's a rad to degree. One thing I want to point out, I've said this before, and you guys don't ever pay attention when I say this, is I will never expect you to use a command in MATLAB that I have not shown you. So when you show me code, I see people do this all the time, showing me code that have all kinds of wacky things. That's cool if you want to do that. I have no problem if you want to learn more about MATLAB, but I'll never expect you to use something that I haven't shown you. All right. You shouldn't, if you're Googling around trying to find stuff, you're looking in the wrong place. You should be able to find it on the Canvas page. All right. I'll never expect you to use something I haven't shown you. All right. But feel free to explore in there. But I think a lot of times when people show me stuff, I think it's the result of some strange searching. All right. Anyway. All right. Questions about what I've done here up to this point? All right. Back to what we were trying to do, right? I'm trying to figure out what the current is in this circuit. So current phasor I equals Vn over ZL plus R. So I did a couple of different calculations here, but here's me trying to figure out the current. All right. So I is 1 over R plus J omega L times Vn. That is exactly this expression. Okay. So I'm just going to take that there and I'm going to evaluate that. And notice what I have here is I took the angle of I times 180 over pi, and then I took the abs of I. So that's going to give me the magnitude, and it's going to give me the angle in degrees. So I evaluate that guy, and I get my answers here. So it tells me that the angle, because I did that first, right? The angle is negative 125 degrees, and the magnitude is 4.7153. So let's try to sketch this stuff. So where is that? If I have negative 126 degrees, where is negative 126 degrees in the complex plane?
The second
Third
quadrant.
quadrant.
Third quadrant, right? Which is over. So negative.
Oh yeah, yeah. Third.
Yeah, negative 125 is going to be down here. It's got a magnitude of 4.7. So it's going to be somewhere, I don't know, around there. Okay. And the angle, remember, angle is always measured from here. So this is negative 126 degrees. And the magnitude is whatever that is, 4.7. Okay. So there's my I. Now, I should probably also sketch where's the Vn at? Where was Vn? We said Vn.
Quadrant 4, negative 45.
Yeah, negative 45 degrees. So that guy was apparently, get that out of the way. That guy was over here. And he's got a magnitude of 3. So this is Vn. Like that. All right. Okay. So, questions about that right there up to that point? All right. So let's say the phasor, is apparently 4.7. I'll round that. I'll say it's 4.72 with an angle of negative 126. Okay. So let's say I want to take that guy and I want to say, well, what would it actually look like if I sketched it in the time domain? So if I wanted to see that current I of t, right, in the real world, right, what would it be? So let's copy that over to another slide. All right. What would this be if I wanted to give me, what's the I of t that goes with this? What would that look like?
It's 4.72 cosine.
Yep, 4.72 cosine with the same frequency. Then what?
Plus 100.
Plus negative 126, right? So I have a negative 126 on that. So in other words, I've just determined what that guy is in the time domain. So if I put in, so what that's saying is if I take this circuit here and I put in this particular input, the current I is going to have the form that I've written right there. Okay. You guys follow that? Much simpler than doing a differential equation. That's the alternative approach. would be to do a differential equation. And that would, as we all agree, would probably be a nightmare. All right.
A question.
Yeah.
The angle for the voltage we said was negative 45 degrees, right?
Yep, that's right.
I thought current and voltage, it was like 90 degrees out of phase.
Okay, you're asking my next question. Okay, so if I wanted to figure out the voltage across the inductor, V sub L, right? V sub L is the voltage across the inductor. So voltage across the inductor. So given this, how do I figure out the voltage across the inductor? Now that I know the current, how can I figure that out? So here's V sub L. How can I figure that out?
Yeah.
Somebody other than Tone.
The V in minus VR.
Well, I could do that, but simpler way.
So we have LDI, LDT.
Simpler way.
The
I
L.
wanna
Voltage
figure out-
divider.
It's the current times the impedance.
Current times the impedance, right? VL is the phasor. So I do I, the phasor, times ZL. So that gives me I times J omega L, like that. Okay. So if I do this means there's two equations, right? So the magnitude of VL is equal to what times what?
Magnitude of I times the magnitude of ZL.
The magnitude of I times the magnitude of ZL, right? So the magnitude of ZL, magnitude of I, what's the magnitude of ZL? Well, it would be omega times L, whatever that is, okay? But the other expression is for the angle, right? The angle of VL is equal to what? How could I get that from this top expression? So it's equal to I times Z. So if I have the product, how do I get their angles?
Wouldn't you just add the angles together?
Yep, that's right. Yeah, I would say angle of I plus angle of Z, like that, right? So angle of I is just whatever that angle is. What's the angle of Z?
90 degrees.
Yeah, if Z equals J omega L, that means this guy points straight up, he said. So he's got a 90-degree angle. So, all right, that gets to, Christian, to your question, right? So if I go back, so what this says in words is the voltage is 90 degrees ahead of the current phasor. The voltage phasor is 90 degrees ahead. All right, so here it is. All right, what should I do here? So there's I. Let me get rid of VN, that's the input. So if I have this relationship, VL, the angle of VL equals the angle of I plus the angle of ZL, which we said was 90 degrees. How do I draw that here? Where would I draw V sub L?
It's quadrant 4.
In quadrant 4, right? And it would be over here, exactly 90 degrees ahead. Right? Because I add 90 degrees and add, this is plus 90 here, right? If I add a positive angle, I'm going to rotate forward. If I had added a negative angle, I would rotate backwards, right? That's the way we add angles in the complex plane. You guys follow that?
So if we're adding angles, it's counterclockwise.
Positive angles always go counterclockwise, right? Because that's the way you think of, positive angles go this direction. Negative angles go that direction. That's a really key concept from trig. Okay. So, and again, the other way to, I could just calculate that straight away, right? I could just say, well, V sub L is equal to whatever I is times J omega L, right? And so I did that myself over in MATLAB, before I do that though, if I'm looking at this picture, if I has an angle of negative 126 and I add 90 to that, all right, what would be the angle here for V sub L? So the angle, remember, is this guy. This is the angle of V sub L. What would that be?
Negative 36.
Yeah, negative 36, right? The angle of this guy would be negative 36 degrees. All right, so let's try that. Let's see if we can verify that for ourselves. So VL, the phasor, is equal to I, the phasor, times j omega L. And I calculated that over in my MATLAB as well. All right, so here it is. VL is j omega L times I. That was my phasor. And I calculated the angle and the magnitude of it. So let's do that. So I do that. I look at my answer. So it's negative 36 degrees and 2.96 volts. Okay. So this guy apparently is 2.96 volts with an angle of negative 36 degrees. Okay. All right. So exactly where we would have said it was going to be. So it totally matches our expectation. So let's say now what I want to do is, let's say I want to look at I of t and V of t together. So VL, we just said, was 2.96 volts and angle negative 36 degrees, right? So if I say, what's VL of t look like? What would VL of t be? The voltage across the inductor.
2.96
Yep.
cosine omega t minus 36 degrees.
Yep, you got it. All right. Now, it may be hard for you to sort of think, well, all right, let me ask you this. Which one, so the term that we use, I'm not going to focus too much on these concepts of leading and lagging. We'll talk about this idea later on. I want to talk about this idea of which one leads and which one lags. It's probably not the easiest thing for you guys to say, what would these look like? 2.96 cosine omega t minus 36 degrees. If I ask you, if I to plot that, well, where would that be? How would you plot that? Where would the peak of that occur? Where would the peak of this waveform occur? Right, the peak of cosine happens at t equal to 0, right? It would look like that. Where would the peak of 2.96 cosine omega t minus 36 be? What angle?
Negative 36. Like
So what do I have to do to cosine to get it to be cosine omega t minus 36? Which direction do I pull cosine?
To
the right?
To the right.
To the right. To the right. So it would be probably something like this. So its peak's going to be over here. Where would the peak of 4.72 cosine omega t minus 126, where would that peak be?
Lagging from there.
It'd be a lot further to the right.
Yeah, it'd be farther over, right? It'd be something like that. All right, so this would be my I, this would be my VL. All right, now because I clearly can't draw, let's take a look at what is happening here. So here's the way I did this in MATLAB. I defined, as I will always do, I gave you a time vector, right? And then I used essentially here, I used the cosine function, and I used the magnitude of the phasor and the angle of the phasor to recreate this guy, okay? And then I plotted them together, all right? So we'll see if it sort of matches our expectation. We'll come back to talking about what I did there, but let's see if it matches our expectation. So here it is, all right? So in this case, I see V sub L is here, all right? And I see that I is here, right? Remember, I was the bigger of the two, right? You guys follow what I did?
Mm-hmm. Yeah.
Now, how can I tell that they're 90 degrees apart from each other? Because we said I and V are 90 degrees apart. How can
Peak of one should be the 0 of the other.
Yeah, the peak of one should be the zero of the other. And I can see here when this guy is at a peak, right? If I draw a line straight down, I see, boom, this guy's at a zero. So they're 90 degrees apart from each other, okay? And that's, that ultimately is something we'll deal with more when we talk about power. In power, we talk about this idea of the phase relationship between current and voltage all the time. All right. And we'll get to that later in the semester. That's all we kind of need to understand for right now. Okay. Questions about that?
And up to here is the test on Friday.
Yeah, that's right. In fact, this solving for a phasor, yeah, this is the hardest thing I would expect you to do. Like a very simple circuit like this. This would be the test on Friday.
Okay.
No mesh or nodal or Thevenin on that. None of that stuff. We haven't talked about that yet. All right. We'll get to that. The next test is going to be all over that stuff. All right. This is pretty straightforward. It's a matter of getting comfortable with the process, I think. Now, looking at that picture, right? Which one of these, where is it? Which one leads and which one lags? So which one is the leading?
Voltage.
Oh, leading, sorry.
Voltage.
Yeah, the red one there
Yeah.
leads, and that's just so happens to be the voltage. So the voltage leads the current. All right. The idea of leading is which one has its peak first. So in this case, it would appear that this guy has its peak first. This guy leads that one. Okay. All right. Seems like you guys are getting those ideas pretty good. All right. So let's look at another one here. So now I've got this guy. Vn is 3 cosine omega t plus 30 degrees. And I have 1 microfarad and 10 ohms. All right. So again, I want to figure out what the current is here. All right. So first thing I do is I'm going to redraw that circuit. So I had, let's see, Vn of t is 3 cosine omega t plus 30 degrees. So Vn of t is 3 cosine omega t plus 30 degrees, like that. All right. So if I want to convert this over into a phasor, first thing I got to do is I got to figure out what omega is in this case. So I was told that the period was 0.001 seconds. So how would I figure out omega if I know the period?
2 pi divided by that.
Yeah, 2 pi divided by that. All right, which is basically 2 pi times 1,000. So what's the frequency F?
So 1 over t.
Yeah, so what is that? 1,000 what? So F is
1,000 cycles per second.
1,000 cycles per second or 1,000 hertz, or 1 what?
1 kilo.
Kilo.
Yeah, and it's kilohertz, not a kilohertz. It's not a wrestling move, right? A megahertz. So it doesn't become singular, right? Once you say kilohertz or megahertz, so it's kilohertz, megahertz, right? So and often you'll hear those numbers: kilohertz, megahertz, gigahertz. Those are pretty common things to use. Okay, so I've got that. I'm going to need omega to calculate ultimately what my impedances are in a second. How do I convert that to a phasor? What's the phasor in this case?
It's 3 angle 30.
It's 3 with an angle of 30 degrees. Okay. All right. So if I'm going to put that into my complex exponential, it becomes that. All right. 3 e to the j 30 degrees. All right. So again, I want to figure out what the current is. So I'm going to say, here's my circuit. All right. This guy is Vn. It's a phasor. And then there's a capacitor here that's represented by a capacitive impedance. And then there's a resistor over here. Okay. So R, and I want to figure out I. Right. Ultimately, I want to know what I of t is, but I'm going to figure out the phasor first. So what would that be?
I is just equal to Vn over the phasor of the capacitor plus the resistance.
Yep, you got it. Right, and Z sub C is what?
1 over J omega C.
Yep, 1 over J omega C, or as often it gets written 1 over, so minus J times 1 over omega C. Right, that works out to be the same thing. That means this guy has an angle of what?
Negative 90 degrees.
Yeah, his angle's negative 90. He points downward. Okay, so again, I did this one here in MATLAB as well. All right, so so I put in, let's look at my numbers here. So I put in 1 microfarad, 10 ohms. So 1 microfarad, 10 ohms. My period was a millisecond. So there's my omega. All right. Now notice here what I did, right? I said 30 degrees. So I converted that here into radians, right? And there's my phasor right there. So if we want to run that real quick. And I say, well, what's the magnitude? So here's V in. All right, V in looks weird, but if I say, what's the magnitude of it? I say, what's the abs of it, right? 3. All right, exactly like we said it was going to be. And then I do the angle of it. All right, that's a weird number. What units are that number?
Radians.
Radians, right? So I want to multiply that by 180 over pi, and it's 30 degrees. Okay, exactly like we said it was going to be. All right. So, all right, there we have it. So if I want to figure out what I is, right, there's I. So here was our expression for it here. We said Vn over Z sub C plus R. So here is 1 over R plus 1 over J omega C. Multiply all that by Vn. Then I get the angle and I get the magnitude. And I plot that. All right. Or I just calculate it first, I guess. So if I look at the numbers I get, so first, this is the angle, 116. This is the magnitude, okay? So that says that I, in this particular case, so 0.0188, what is that in milliamps?
18.8.
Yeah, 18.8 milliamps with an angle of 116 degrees. All right. Where is 116 degrees?
Second quadrant.
Second quadrant, yep. So this guy would be somewhere over here. So this is I in this case. All right. Now, let's say I wanted to figure out where V was going to be, the voltage on the capacitor, right? How do I figure out the voltage on the capacitor in this circuit? So there's my circuit. How do I figure out the voltage on the capacitor?
Like the actual magnitude value, or where it will be on the graph?
Where it would be on the graph. Let's just think through where it would be on the graph. So if let's just say I want to figure out the phasor for it, right? If I want to figure out the phasor for it, V sub C is equal to what?
V sub C, isn't that the minus J over 1 over C?
Yeah. Just I times Z sub C, right?
Okay.
And Z sub C we said was what?
Negative J 1 over C. I mean 1 over W.
I times basically 1 over J omega C. You could do it with a negative like that. But if I go through that whole process, right, that says that the magnitude is the product of the magnitudes. And the angle of V sub C is equal to what?
It's I.
Angle of I minus angle of Z.
Angle of I plus the angle of Z. Right?
Yes.
What's the angle of Z in this case?
90 degrees.
Negative 90. Right? So that says if I want to figure out where the voltage is going to be, what do I do?
You got to rotate it negative 90 degrees.
Negative 90 degrees. So there's I right there. Where's V going to be?
On the first quadrant.
First quadrant. That's right. It's going to be over here. All right. So this guy here had an angle of 116 degrees, right? We said this guy was 0.0188 with an angle of 116 degrees. So what's this guy's angle going to be?
It's just
26.
Or 26,
Yeah, 116 minus 90 should be about 26. Okay. So let's do that real quick here. All right. So here's where I did the math. And let's run that. And there it is. Okay, there's the angle, 26 degrees, and the magnitude is apparently about 3 volts. Okay. So my scales are way off here. That means this guy is way bigger. Right? This was 18 milliamps. This guy's 3 volts. Right? My scale is still pretty far off, but this guy is a 90-degree rotation. So in this particular case, right? If I were to sketch these things, what I would see is that the voltage in this case leads the current, whereas in the inductor, the current leads the voltage. I'm not going to say a whole lot about that leading and lagging thing. Right? What I want you guys to understand is basically everything we just went through. Okay. So hopefully you feel a little bit more comfortable about what we just did with those 2 examples. All right. We're going to keep doing more of that and sort of expanding on this in the next couple of lectures. All right. Questions, guys?
Nope.
All right.
You're going to post this, sir, correct?
I will. That's correct.